So good morning friends. So the whole solution topic is at a glance for you. So in this topic we studied these concepts and just we going to discuss short rather than short just we discuss look after one by one. So in solution topic first we studied the introductory part. So introduction we see the what is meant by solute, what is meant by solvent, isn't it? Saturated solution, unsaturated solution, supersaturated solution, isn't it? True solutions, all these things we studied, isn't it? Then we see the types of solutions. So depending upon the which factor is more and less on that points, we classify the solutions into 9 types, isn't it? Solute, solvent, in this way by changing we classify the solution in 9 types. So there are 9 types of solutions and their examples. Then capacity of solution to dissolve solute. So in this case, we studied the given solution accommodate how much amount of solute, isn't it, to prepare a solution, or to for rather than to form a saturated solution, to form a saturated solution, isn't it? Let's just next we see the solubility. We see the solubility. Actually, this is the definition: capacity of solute, capacity of solution, capacity of solvent to dissolve solute is the definition of solute at given temperature, at constant temperature. Under the solubility point, we studied the factors affecting solubility, isn't it? What is the factor effect of nature of solute and solvent, isn't it? Nature of solute and solvent, effect of temperature, effect of pressure, isn't it? All these things we studied. And under the effect of pressure, under the effect of pressure on solubility of gaseous solute in liquid solvent, we studied in detail the Henry's law, isn't it? S is equal to Kp. S is equal to, that is solubility is equal to Kh into P. It is the Kh is the Henry's constant, isn't it? Henry's law constant. And we study the examples and also numericals on to calculate either solubility or Henry's constant or pressure over that solutions. Then Raoult's law. Under Raoult's law, we studied the vapor pressure of solution and that of the solvent, which has more vapor pressure. Solvent always has more vapor pressure rather than solution one. Why? Because in solvent there is a only one kind of all molecules are there. There is a one kind of force uniform. There is a force of interaction. But when you prepare a solution, there is a mixing of solute and solvent. Then there is a intermolecular interactions are 2 types one, isn't it? And due to that, we consider here in this topic solvent is volatile, isn't it? That's why solvent has always more vapor pressure than solutions. And also we see the in Raoult's law, we derivation also Raoult's law for a non-volatile solute and for volatile solute, isn't it? Then ideal and non-ideal solutions. So what is ideal solutions? What is non-ideal solutions? We classify depending upon the what sort of interactions between A dash A, B dash B, and A dash B. Now, less than, more than, greater than, less than. On that criteria, we classify ideal and non-ideal solutions. Isn't their characteristics also we studied one, and depending upon that, again we further classify that the solution shows 2 types of deviations, isn't it? For non-ideal, 2 types of deviations. There is a positive deviations and negative deviations. Graphically also we complete that. Then we see the colligative properties, definitions of colligative properties. That is, the colligative properties are those properties which depends only on number of fluid particles, not on their nature, not on their nature. फक्त सोल्युशन असणारे किती पार्टिकल्स आहेत, नंबर्स महत्त्वाचे. Then under colligative property we studied 4 types of colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. And there are also derivations of each with graphical representation. With graphical representations. In this case there is a no any constant is there, but boiling point elevation there is a constant Kb that is called as molar elevation boiling point constant or ebullioscopic constant, has unit Kelvin kilogram per mole, isn't it? And also numericals seen in the last lecture. Freezing point depression Kf cryoscopic constant or molar depression freezing point constant, isn't it? And note well that in this in all the cases here just m molarity, m molarity. So whenever you elaborate the small m, that is molarity terms, try to write always that is the weight of solvent in kilogram, weight of solvent in kilogram, remember well for from here onwards. Then osmotic pressure pi is equal to mrt or pi is equal to crt, so it is from ideal gas solution we derived that is pi v is equal to nrt. Then colligative properties for electrolyte solutions, isn't it? Still now we see the non-electrolyte, but from here, what is the difference between if you prepare a solution of similar concentration for a electrolyte and similar concentration for non-electrolyte. That is the colligative properties, whether they are same or different. The colligative properties are different, isn't it? Now, why different? Because the electrolytes and non-electrolytes, if you mix the electrolyte in water and non-electrolyte in water also, then their ionization capacity, rather than ionization, electrolyte dissociates to form ions, but non-electrolyte does not dissociates. And that is the one of the basic concept, that the colligative properties values depends only on the number. So electrolyte number increases, so it affects on the colligative property, but in non-electrolyte number remains same, so it will does not affect their colligative properties. Then we see the Van't Hoff factor I. Van't Hoff factor I, that is the Van't Hoff scientist try to relate the colligative property for electrolyte and non-electrolyte solutions. Electrolyte and non-electrolyte solutions. So that's why we modified equation and write like this: delta TB is equal to IKBM. Delta TF is equal to IKF into M. Pi is equal to IMRT or ICRT. IMRT or ICRT. This I stands for Van't Hoff factor. So it is applicable for both colligative as well as electrolyte as well as non-electrolyte solutions. Then we see the modified expression. This is the modified expression for Van't Hoff factor, isn't it? And lastly, we see how the one can determine the degree of dissociation by measuring the Van't Hoff factor I for weak electrolyte, isn't it? So in this way, just study the topics from beginning up to the end. Whatever concepts are there, just study by heart rather than by heart. First, try to understand, try to remember the formulas, graphs, definitions, and then try to solve the examples, isn't it? And by practicing regularly, chemistry becomes very easy. Okay, good day.